All right, today we're going to get into just some practice of related rates. We're just going to apply what we did on the previous problems from the previous lecture. We're going to still apply those same strategies, and we're just going to kind of approach some are going to be word problems, some are going to be a little bit more straightforward, but we're still going to pull in that implicit differentiation to solve these. So this is just a repeat of our strategy for related rates. Understand the problem. What's it asking? Do I need to draw a picture? If that's going to help, do I need to name my variables? Well, you should always name your variables. And then capture the value of the variables, meaning if it's an object that's moving through space, how much time has passed, or what is the object? It's like either like X coordinate or Y coordinate in space, something like that. Identify what you're trying to find. Again, it's Calc 1, so more than likely, I need a derivative. So, first things first, which derivative are you trying to find? Now, and if you're trying to find the derivative, make sure you know what you're after. So, what I mean by that is, if it says the length is changing, don't go out and say, oh, well, I already know what the width is changing. That's great. You might need to use it, but you need to capture the values that are asked. Now, be careful of some wording. Remember, like with the last one, or in the last lecture, I talked about, it said, there was a problem that said if the area is to remain constant. That's one of those things that you have to be careful of, because it means the area remains constant, its derivative is 0, because it's not going to change. If it says something is increasing, getting larger, or decreasing or shrinking, you have to know, does that rate of change, is it positive or negative? So when you capture values, that's one thing you have to go back to that right quick. That's one thing you want to keep in mind. Write equations that relate to the named elements. You're not always given, okay, here's the problem, here's the equation, go find the derivative and have a good day. Sometimes you may have to set them up. Again, the related part in related rates just sometimes will mean how are the rates of change related, but it can also mean what formulas relate to it. So make sure that you know just kind of like some of the basic geometric formulas. So like area and volume are good ones to know. So you may need to combine some of these rates of change to get a single relationship. So it may be a case where like the rate of change of, like let's say it's the rate of change of like a box. So you know the length, the width, and the height. And maybe the area is constant or the length is constant. Then you have to know how to do product rule on that and be able to figure some of those things out. So you want to differentiate with respect to t, because again, these are things moving through time. There are going to be functions that when you think about them, you go, okay, at what time did this occur? Then once you've figured out your derivative, you've solved for it, then you can plug in your values and you can answer your question. And then again, beware of your units and signs. That's why I focus on, is it increasing or decreasing, growing or shrinking? That's going to tell you that positive and negative part that you have to be aware of. So keep those in mind. So for our first example, so again, we use Thomas Calculus. So this is page 163, number 39. So a ball falls 16 t squared feet in t seconds. Again, if you were to convert, gravity is roughly 32 feet per second. So that's kind of where this is coming from. So how fast is the shadow moving at t equals 1/2 of a second? key focus here. Ball falls at 16 t squared feet in t seconds. So let's identify what we've got. First of all, here's the ball at t equals 0. I'll try and just draw it as a dotted line and then make it solid through here. Now again, I want to emphasize the related part of the related rates. And the thing is, I'm no artist. So imagine this is a straight line. From here to here, I know that it's fallen 16 t squared feet at that point. That's how fast it's falling. So then I know that if it's 30 feet away from the lamppost here, this also has to be 30 feet. So notice x of t is the shadow. So that means this whole length is x. And if I'm looking at a 50-foot pole, then so here's 50. If it's fallen for half of a second, then let's see. You don't want to use specifically, could I plug this in and figure out a value? Yes, but it doesn't help me. What will help me though is using this component. Because to go back to a little trig, this angle and this angle should be the same because there'll be parallel lines that are cut by a transversal. So these angles should be the same thing. And notice here, what do I have? I have, if you think about this one, I have a base and a height, and I have a base and a height. So this should mean that to use similar triangles, that idea. So in reality, I didn't need that part. So what I've got here is a relation that x is to 50 is 30 is to 16t squared. And so if you're looking at that and going, well, how was I supposed to get that? It's all about using the components that you have. All I did at first was identify, okay, what can I work with? Because if you go back to the original picture, we don't have this 30 up here, and we don't have that this is 16t squared feet. And again, you don't want to think about it as 50 minus 16t squared. Think about this kind of as the ball is falling down. So if this was a triangle, this would be a positive length, not a negative length. So I drew this line, and I used the fact that we knew the ball was 30 feet away to make this picture here. So I said, okay, well, I know from the light to where the ball started was 30 feet. We're assuming it's falling straight down and like a giant gust of wind does not come by and throw it off course. Then, it sounded like a teenager, or sounded like I was going through puberty for a second. So 30 and 16t squared. Because remember, from here, it falls for t seconds and it moves 16t squared feet. Now, if you wanted to know what the actual height was, you would do 50 minus 16t squared. But what I know is that 30 plus the 16 t squared feet should give me this 50. Or not 30, sorry. I know that this is 16 t squared feet, and that at some point I will have fallen below 50. And so I can figure out, if I plug in whatever value, I can figure out how high off the ground the ball is. But the key thing is, I need to use what I've got. And so I can use similar triangles. This whole thing is the length of the shadow. And so it's going to be x. And then the height is fixed of the pole, it's 50. So you have you could do opposite over adjacent or adjacent over opposite. You would still work in the same, or you would still get the same thing. I just decided, because I know I'm going to want x in the numerator eventually, it would probably be better to keep x out of the denominator. So you could have done 50 over x is equal to 16t squared over 30, but that doesn't really help you in the long run. So now I'm going to get x by itself, because remember, I care about the rate of change of the shadow. So if I multiply both sides by 50, I get x is equal to 1500 over 16. And then what I'm going to do is I'm going to make this t to the negative 2, just to make life a little bit easier. Because I would rather have this part and not have to deal with anything else. Or I would rather not have to do a quotient rule. Let me be more specific. I'm being lazy here. I don't want to have to do the chain rule, or not the chain rule, the quotient rule. So I'm just going to turn it into a constant times a variable to a power, because life's going to work a little bit easier that way. So now I have x on this side, t on this side. So then let's just take the derivative with respect to t of both sides. So then I get dx dt is equal to so if I do the derivative with respect to t of 1500 over 16 times t to the negative 2, that's going to get me dx dt is equal to 1500 over 16 times negative 2 times t to the negative 3. And so I now know the rate of change of the shadow. And at this point, it worked out very nicely, because I didn't have to, or now technically I could find the rate of change of the shadow at any point. So that's actually really helpful. But key thing here, I need to know how fast is it moving at 1/2 of a second. So if I do dx dt and I evaluate that at t equals 1/2, then I'm going to get 1500 over 16 times negative 2 times, if you cube 1/2, you get 1/8. And remember, this is t to the negative 1/3. So this is really, if I do 1/2 to the negative third, I get 1/8 to the negative 1, which is just 8th, or 8, not 8th. Which you can see, this is part of the reason why I did not reduce. I knew what I was going to get in the end. Now, if you don't know, it might be easier just along the way to reduce where you can. You don't have to. Sometimes it's going to be preferential, though. I just knew what I was after. So if you reduce throughout the way, that's okay, too. And that's going to give me just that dx dt at 1/2 seconds is negative 1,500, don't forget your units, feet per second. And we know that because, again, the shadow is moving. It's a velocity of the shadow. So it's moving at 16 t, or it falls at 16 t squared feet, and then its time is in seconds. So that makes it pretty easy. I need to use feet per second. Now, if you're thinking 1,500 feet seems very fast, yeah, it kind of is. But you have to keep in mind, if you think back to this being just like a straight line, if you take that straight line, I was about to try and do a motion with my hand that you're not going to be able to see. So if you take the straight line and you bend it just a little bit, it goes from the lines never intersecting to the line, or what I should say, the red line here and our x-axis here. These never intersect. But if you rotate at this angle theta, after 1/2 second, you've gone from them never intersecting to them intersecting at some point over here. So negative 1,500 feet per second for just a ball is pretty fast, but if you keep in mind about the way the angle is going, it makes a lot of sense. So don't let that one be too confusing and going, that seems pretty fast. Yes, it is, but in the context of the problem, it makes a lot of sense. All right, so if you have ice that's around a sphere, let's see what we have. So you have an 8-inch diameter iron ball, and it's covered with ice that's 2 inches thick. And the ice is melting at 10 cubic inches per minute. So how fast is the actual ball melting? So first of all, let's identify some pieces about this. Volume of a sphere is 4/3 pi r cubed. That one's not too bad. We at least have that to go off of. But the thing you have to keep in mind is this is 2 separate layers. It's the non-changing layer of the ball and the ever shrinking layer of the outer part of ice. So what we have is this is 2 inches thick, and the diameter of the iron ball is 8 inches thick. So when you put them together, you get the full radius. So the thing I have to keep in mind is what's actually changing. The iron ball in the middle is going to change, or is not going to change as the ice melts. So you do have to keep that in mind. And I'll show you how I know it's not going to melt, even though you're thinking, okay, well, what if it was just a giant sphere of ice? Then that would actually change some things. So we'll do, this is going to be 4 pi thirds. The radius, we'll call this R0 for the radius of the outer, minus 4 pi thirds the radius, and then we'll call this part the inner radius. And that's still going to be cubed. So next what I can do is I need to take derivatives because I need to know how fast is the ice thickness decreasing. The ice thickness is the outer layer, not the inner layer. So we're technically looking for the rate of change of, sorry about that. We're looking for the outer layer's rate of change. And we know how fast it's melting. So let's take the derivative with respect to time of both sides. So dv dt is equal to 4 pi thirds, that's not going to change, times 3 r naught squared. Because remember, r naught is our, or I shouldn't say r naught, that makes it sound like a constant. R0 is our outer radius, and then times dr0 dt minus 4 pi thirds, and then times 3 ri squared times dri dt. This is where it gets important because if I can find a color that I haven't already used, the inner radius is constant. The iron ball is not changing as time goes on. So if it's not changing, this rate of change is 0. So in this case, we still only had to look at the outer radius. Even if we had left as 4 thirds pi r cubed, we would still be needing to look at this 2 inches of thickness in the actual radius. So now we can actually plug in some values and get something out of it. So this would be, now it said the ice is melting at 10 cubic inches per minute. So that means that the volume is changing at 10 cubic inches per minute. And that's going to be equal to 4 pi thirds. Well, actually, those would cancel up here. So let's just make this a little bit easier to deal with. This is going to be 4 pi times the outer radius, which is 2, which we're squaring, times dr naught dt. So that means our radius is going to be equal to, or the rate of change of our radius is going to be, so this would be 10 over 16 pi. Now, what would the units be? Keep in mind, the volume is changing at 10 inches cubed per minute. However, we have the outer radius because the outer radius tells us how much is it shrinking. So technically, because we're talking about the ice's thickness and not the total overall, so if I threw units onto here, this is 10 inches cubed per minute. And this is equal to, if I go ahead and multiply it out, this is going to be 16 pi inches squared times our dr naught dt. So notice when you divide here, you would have inches cubed per minute, and then the inches squared goes in the denominator. So that's actually going to cancel, and you're going to get it's 10 inches, or 10 over 16 pi inches per minute, because it is telling about the radius. So how fast is the ice thickness decreasing is also asking, because it's uniformly melting around it, you can identify it by how fast is the radius shrinking. Now, by the context of the problem, it's okay to say it's decreasing at a rate of 10 over 16 pi inches per minute when the ice is 2 inches thick. You don't want to say it's decreasing at negative 10 over 16 pi inches per minute, because if it's decreasing in a negative direction, that actually means it's increasing. So you can either say the rate of change is negative 10 over 16 pi inches per minute, or the better way to say it is, I should have done this for the other one. When if I can spell. All right, so this is probably the best way to answer it. When the ice is 2 inches thick, the thickness is decreasing at 10 over 16 pi inches per minute. So, as a word problem, probably best to give a word answer. But this is how you would go about it. Now, notice if we had just started with 4 pi r cubed, the problem is if you try and treat it as just 4 pi r cubed, the whole ball is not changing in the same way. That's why we had to split it up into the outer radius and the inner radius. So that was where all this came into play, where the derivative of the inner radius was actually 0, because it's a solid metal ball. It's not going to change as the ice melts. And on to the last problem. So, building shadow. So, on the morning of a day when the sun will pass directly overhead, the shadow of an 80-foot building on level ground is 60 feet long. At the moment in question, the angle theta the sun makes with the ground is increasing a rate of 0.27 degrees per minute. At what rate is the shadow decreasing? Now, this is kind of one of those little facetious things to do. Remember to use radians and express your answer in inches per minute. So, first thing we have to do, so it tells us at the start, the angle theta is increasing at a rate of 0.27 degrees per minute. So the rate of change of the angle theta as time goes on is 0.27 degrees for every 1 minute. I need this to be, though, in radians. So I'm going to multiply by pi radians over 180 degrees. And then this is going to equal the angle, or the rate of change of the angle theta we're going to use is actually going to be 3 pi over 2,000 radians per minute. So we got the first thing out of the way. Now let's start identifying some of the other problems we have. So first thing I want to do is identify what I'm after. And I'm after the rate of change, the shadow. So kind of like the first problem. So again, we need to identify. We're going to call our shadow just x. So now let's see what I can do with that. Well, I've got an angle, and I have an opposite side, and I have an adjacent side. So if we go back to our trig functions, then tangent of theta is equal to the opposite side over the adjacent. So now I have something I can work with. And to make it something that I want to work with more, because I know I'm going to have to take a derivative, anytime you can avoid having to do a quotient rule, just do it. Or avoid doing a chain rule, make life easier on yourself. You don't have to do all the work if you can just plot it out a little bit careful from the beginning. So tangent of theta equals 80 times x to the negative 1. Cool. So this is going to be differentiate with respect to t. So if I do that, derivative of tangent of theta is secant squared theta. Again, the variables do not match, so our d theta dt term pops out. And then we get 80 times negative x to the negative 2. Variables don't match, so I get dx dt. And this is what I'm after. I need to know at what rate is the shadow decreasing. So in this case, I got dx dt. I know at that particular time, the shadow along the ground is 60 feet long. So that's cool. I have that I can work with. So first things first, let's identify or let's get dx dt by itself. So if I do that, I'm going to get, so this will be negative 80 over x squared dx dt. So then I'm going to multiply both sides by x squared over negative 80. So this will give me x squared divided by negative 80 times secant squared theta times d theta dt, which equals dx dt. Cool. I know what x is at the given time. I know the rate of change of theta. That was the first thing that we actually identified. Actually, they were nice enough to give us that. But the problem is this secant squared theta. What is the secant squared? Or not even just what is secant squared, what's secant? I'm not given an angle So I can't find it. But what we can do is we're going to use that information again that the shadow is 60 feet long. So if I do that over here, and I make this, so here's theta. This is 80 feet. Imagine I have artistic skills and drew a right angle. This is 60 feet. So if we use the Pythagorean theorem, let's say this is our hypotenuse. So h squared will equal 60 squared plus 80 squared. Which that's going to give you that h is equal to 100. Whoops. So you take the square root because it would be 3600 plus 6400. Add those together. And then you end up, take the square root of that, you get 100. Now the other way is a quick little aside, is this is a specific case of a what's referred to as a 3, 4, 5 triangle, right triangle. So if you notice, 60 is 3 times 20, 80 is 4 times 20, and 100 is 5 times 20. So this is just a scaled up version of this 3, 4, 5 triangle I drew up in the top left corner. So anytime you have a right triangle and it's got a 3, 4, and a 5, and they meet that scaling factor, they both have the same scaling factor. So let's say you took this triangle and you multiplied everything by 3. A 9, 12, 15 is just a 3, 4, 5 with that particular scaling factor. But anyway, back to this problem. So remember your relations, that sine is related to cosecant, cosine is related to secant, and tangent's related to cotangent. So I don't necessarily have the secant, but I could find the cosine for this triangle. So my cosine of theta is going to be this. So remember, it's adjacent over hypotenuse, so it's 60 over 100. So cosine of theta is just 3 over 5. And so if secant is 1 over cosine, that means that secant of theta is just 5 over 3. Just using those trig identities. Cosine is adjacent over hypotenuse. Secant is hypotenuse over adjacent. So technically, you could have done that too and still got to the same result. But now we're in a good spot because now we can just kind of click through. Now we can just plug in all of the values. So that means dx dt is equal to, so x at the given time is 60. So I get 60 squared divided by, so let's see. So we get 60 squared divided by negative 80 times, this is secant squared, so this is 5/3 squared, times 3 pi over 2,000 and after all of that, that will equal negative 9 pi over 4, as long as I didn't make a stupid math error. Negative 9 pi over 4 feet per minute. So again, it's decreasing, so it makes sense that we're saying it's okay to say negative 9 pi over 4. If we go back to this one, knowing the context is important because you could say, well, why didn't this one come out negative? It's in the way we set it up. We didn't say that the rate of change is increasing, we said it's decreasing. So as long as you know the context, it's it makes the problem go a little bit smoother. Because technically what I should have said is if it was melting, I could have used negative 10. So, and that would have given us the negative value. So just make that little, let me make that little addendum here. So that's where I went wrong with that one. And then again, it's a word problem, so it'll get a word solution. So the shadow is decreasing at a rate of negative 9 pi over 4 feet per minute. And this is how I would want you to leave it. Don't round it to some decimal or anything. This is exact. If this was like a job site or something like that where they needed to know kind of an approximation, yes, give an estimation. But for the exactness, just leave it as that for now. So that covers all of our related rates. Again, these are good problems because they are purely application. This will always be well, when am I ever going to use this in the real world? Here are some examples. And you may go, well, some of these questions seem stupid to ask, but they're analogous to some actual good problems. So with that, we'll do 3.9 next, and that'll wrap up chapter 3. So practice hard on these, and I'll see y'all in the next one. And keep the notations.